Okay, let us discuss data compression. So as we said, you can quantify the amount of information that a random variable contains by finding the best way of representing this random variable in terms of bits of strings, and by asking what is the mapping between the values of the random variable and strings of bits that minimizes the expected length of the bit string that you want to that you expect to have. So this means that essentially we are looking at optimal representation of a random variable in terms of strings of bits, and these representations are called codes. So a code, as we said, is a mapping between the values of random variables and a string of zeros and ones. It can also be, you can also choose a different alphabet, with instead of zeros and ones you can use more digits, but let's just discuss binary coding. And these strings of bits are called the code words. Okay, so each of these code words has a length L of x, which is equal to the number of bits in code word C of x. Okay. So as we have said, we have already encountered one code when we were discussing Shannon theorem, and there essentially the problem was to find a way to code messages. So a message is a sequence of words. So essentially, in information theory or in coding theory, X are called words, and messages are just sequence of words, which is let's say just sequence of n words. And what we have seen is that in Shannon theorem we have already found a code for messages produced as where these xi are independent and identically distributed words from a distribution P of x from a given alphabet. Okay, this is sometimes called the alphabet. So actually words are sometimes called characters, and okay, so and these characters are drawn from a certain alphabet, And what we said what we have seen in Shannon theorem is that essentially you can find an efficient code for messages of n random variables by counting all the typical messages. You fix an epsilon, you compute the set, you define a set of epsilon typical messages, which is the set of messages such that the probability of the whole message is close to e to the minus n times the entropy. And the asymptotic equipartition property ensures that almost surely messages will belong to this set, so you only have to code messages that belong to this set, and you can just number them from 1 to the number of messages in the epsilon typical set, and look at the code word which is the binary representation of this number. Okay? Now this is not very efficient because if you have to do it in practice, you should compute, you should list all these messages, these possible messages. These are exponentially many. And instead, what one would like to have is a message, are code words for messages that can be expressed in as a sequence of the code words for the individual characters. Okay. So that if you think of this as a string of bits, okay. So you want that when you read this string of bits, you can figure out what is the code word for character 1, what is the code word for character 2, etc., etc. Okay. So, so you want to build, the idea is that you want to build code words for messages from, so the codes for messages from the code for characters, okay? And we have already seen a couple of examples of codes. So a code, so let's take the example where my random variable x can take values a, b, c, or d. So we have seen a particular code c of x where we have assigned to a the code word 1, to b the code word 0, 1, to c the code word 0, 0, 1, and to d the code word 0, 0, 0. Okay? So these are 4 different code words, and they allow you to decode this string of any string into a sequence of characters. Okay, so for example, because you know that code words for characters are at most 3 bits long, and they, if they are less or equal than 3, then they end with a 1. Okay? So, for example, if you look at this message here, so this would correspond to a C, and then here you have a 1, a 0, 1, which corresponds to a B. Then you have a 0, 0, 1 that corresponds to another C. Then this one would correspond to an A, this one to another A, and so on. So you can read this sequence, if you define this code here for characters, then you can read this message and the string of bits and just decode directly what is the string of characters. Okay. So we would like to have, we would like to study codes of these types. These are not the only codes that one can consider. Say, for example, you can consider a code which is well, you can consider another code which is the one we have seen, the one where A is 1, B is 1, 0, this is 0, 1, and this is 0, 0. So this is another code that we have discussed. But you can consider also codes where, say, for example, here you have 0, 0, 1 that corresponds to a particular code. And this would also be a code that allows you to decode your sequence. There are other codes that instead say, if you define another code as, say, 0, 0, 1, 0, 1, 0, and 0, 1. So, for example, you can see that, well, this code has a problem because when you encounter a 0, 1, then you don't know whether you are dealing with a B or whether you are dealing with a D. Okay, so so in order to figure out whether the sequence in the sequence you have a B or a D, you should look at how you can decode the next sequence. So, for example, let's see if in this example, and also here you see that when you have a 0, you don't know whether this is an A or a B or the beginning of a B or the beginning of a D. Okay, so in some sense these are the type of codes that you would like to study, and these codes have the particular property that they're called instantaneous code. And they have the particular property that no code word is a prefix of any other code word. Okay, so for example, here you see that this code word here is the prefix of this code word here. So it's the initial part of this code word here. And also this code word here, 0, is the prefix of these two code words here. So this is not an instantaneous code because it does not allow you to decode a sequence of bits instantaneously. Okay? Instead, if you have a code where no code word is a prefix to any other code words, then you can decode any string of bits instantaneously as you run through it. Okay? Very good. So the distinguishing feature of instantaneous codes is that you can represent them in a binary tree, where if you start from the first digit and then you go to the right, then you can just put this code words on a binary tree. So for example, in A, here there will be A, then here there will be B, well this is again 0 and this is 1. Here there will be B, and here there will be C. Okay? Now you see that explicitly the fact that any code word corresponds to a leaf of this tree, and there is no code word that is an ancestor of any other code word. So if you go from a code word up to the root, then you never encounter any other code word. Okay, so this is a property of instantaneous code, and this is actually necessary and sufficient condition for a code to be an instantaneous code. Now the key property of instantaneous codes is that they satisfy what is called Kraft inequality. Okay, so if a code is an instantaneous code, is an instantaneous code, then the sum over all the characters in the alphabet of 2 to the minus the length of code word x is less or equal to 1. Where this L of x is equal to the length of code word x, okay? And so, for example, here L of A will be equal to 1, L of B will be equal to 2, etc. Okay? So this is a general inequality that instantaneous codes satisfy, and the converse is also true, that if L of x satisfies this inequality here, then there is an instantaneous code which is instantaneous, with this code length. Okay? So, very good. So let us see how the proof of this inequality is very simple, because what you can do is to complete, so look at what is the maximal depth of this tree. For any code you can compute what is the maximal depth of this tree, and you can just compute for any code words how many descendants each code word has up to the maximal depth. Okay, So in this case, for example, A will have 4 descendants, B will have 2 descendants, and D and C will have none. Okay? So in general, if L max is the maximal depth, then the number of descendants of x will be 2 to the L max minus L of x. Okay? Because, say, if a node is at depth L, then the number of nodes at depth L max will be equal to 2 to the L minus L max. 2 to the L max minus L. Okay, so now if you look at, if you sum all these descendants here, so all these descendants they should be less or equal to the total number of nodes at depth L max, but these are just 2 to the L max. Okay. So then you see that if you divide by 2 to the L max, you just get this inequality. Okay. Now, essentially, we can go back to the problem of optimal coding and see again how we can solve it. So the problem of optimal coding is the one of minimizing, finding the code that minimizing the expected value of the length of the code word. But now we know that code words should be, and we want to minimize over all instantaneous codes. So we know that all instantaneous codes are all the codes that satisfies this inequality. So we want to do this minimization subject to Kraft inequality. Okay, subject to that condition. Okay, so how do we do this? Well, we build, we rewrite this as a minimum with Lagrange multiplier on C and on lambda of the expected value of the length minus lambda times Kraft inequality, which is 2 to the minus L of x minus 1. And if I minimize over C and lambda, then I will meet this constraint with an equality. So notice here that the codes which have the shortest code words are those that are closer to saturate this inequality, to make this inequality an equality. Okay, and okay, so now the problem of this is that we should optimize, solve this problem on discrete values of L, and which is a little bit complicated. So let us solve this problem, and assuming that L of x are real. Okay, so if we find the minimum over this problem when L is a real random variable, then we will find a lower bound to this problem here. Okay, so if we assume that L of x is a real random variable, then we can take a derivative here, and if we take a derivative with respect to L of x of this expression, what we get is just P of x minus lambda, actually plus lambda log 2 log of 2 times 2 to the minus L of x. Okay, and if we set this equal to 0, then well, first of all we can find what is the value of lambda. So if we sum over x this equation here we get 1 from the sum over x of P of x plus lambda times log 2, and if we want to saturate Kraft inequality, then this also gives us 1. Okay, so this equation tells us that lambda will be equal minus 1 over log 2. Okay, so it essentially means that this factor here is minus 1. Okay, so then this equation means that P of x minus 2 to the minus L of x is equal to 0, or that N of x, L star of x, is equal to minus log base 2 of P of x. Okay, and now if you take this equation, then you find that the expected value of the length of this code is actually equal to the expected value minus log of the probability of x, which is exactly equal to the end of x. Okay. Now, as I told you, the optimal L has to be an integer. So essentially, what you find is that the minimum possible value of this must be larger or equal than the entropy. Okay, but you can also show that if this is a real value, a real integer is a real takes a real value, you can take the integer which is the largest integer, the smallest integer which is larger than L star of x, and by this you can show that this must be equal to less or equal than entropy plus 1. Okay, so essentially you can show that if you take instantaneous codes, then for each character, then you can achieve a code that that is close to the entropy. So it's between the entropy plus 1 and the entropy and the entropy. Okay. Now, you can see also that So if instead of coding just one character at a time, I look at instantaneous codes for messages of n characters, then I have the same, I can write the same inequality for messages of n characters. And well, the idea is now that instead of looking at instantaneous codes for just a single character, I look at instantaneous codes for n characters where these xi are iib. Okay? So then I can, for an instantaneous codes for the for messages which is formed like this, then I can show by the same argument that this inequality occurs. And but I know that this is equal to n times h of a single character, and this must be larger or equal than the minimum of c of the length of the code of the whole message. So this is is larger or equal and h of x. And now if I divide by n, then what one can show is that for n going to infinity, the minimal length of the code words per characters or bits per characters that I need essentially is equal to the entropy, and this is the same statement of Shannon theorem. So you can show that 1 over n minimum number of characters, number of bits that I need per character for long messages as n goes to infinity goes to converges to the entropy per characters. Okay, and this is exactly equal to Shannon theorem. Okay, so this is this subject is discussed in much more detail in the book of Cover and Thomas in chapter 5. There you also find examples of codes of how you, given a probability distribution, how you design a code that is optimal. And the idea generally is based on this equation here, that you should always use long code words for infrequent characters. So if X has a very small probability, then you should assign to it a code word which is longer. And if X has a small probability, then you should assign to X a short code word. Okay? So for example, one efficient code that is discussed in cover is what is called Huffman code, and there essentially you start from the most you start building this tree, this binary tree that I told you by the bottom. So you start with the most, you take the two most infrequent, the two values of X which have the least probability, and then you assign one a 0 and to the other one 1. Then you take this node and you take the lead, so this means that this node will correspond to a probability which is the sum of these two probabilities. Then you take you take the next two least frequent values of X and you merge them together. And you build your tree in this way, always merging the two least probable characters that you have. And in this way you can build an instantaneous code, because the tree that you will build will have all the characters will be in the end nodes, and you can show that this is an optimal way of building codes. And okay, but I'll refer to Cover and Thomas if you want to see more details.